Swayam Prabha. Digital India. Educated India.
Welcome back. In the third lecture of module 1, we will be continuing with our discussion. Here we will be looking at some of the evolutionary aspects of operating systems, how operating system evolved over the time, starting from the most primitive forms of operating system in the earlier days to the kind of so called modern operating systems that we see today. Okay. So, the topic is evolution of operating systems. Let us start with the most fundamental type of operating system that was available in the first generation of computer systems in the late 60s and early 70s, you can say. These were called batch processing system. At that time, computer systems were very expensive, the hardware was expensive and the size of the computers were very large. The users were not allowed to come near to the computer. There were people called computer operators. They were specially trained, they knew how to operate the computers, and the input output mechanism was entirely different. See, today we all sit in front of a terminal, see our results on the screen, we type on the keyboard. That time it was entirely different. Whatever program we wanted to run, we had to type it on some kind of a punched card or punched tape. There were separate machines for those. We had to sit there, type our program, create our deck of punched card or punched tape, and then go and give it to the operator. The operator will run those programs later on, and maybe next day we come back and take the output as a printed sheet. Okay. Now, some of the characteristics of those machines, the batch processing system of the earlier days was, first thing, it was a single user system. At a given time, only one user was used to run his or her program on the system. And as I said, the size of the machines were pretty large. They used to fill large rooms, they used to consume enormous amount of power and so on. They were large machines, they were run by operators through some consoles. There are a lot of switches and other things, they used to run those through those consoles. As I said, the input mechanism, the way the computer was reading the data or the program to be run was through paper tape or punched cards. Okay. So, in this kind of machines, you see, once we submit, let us say, the punched card. So, there was a card, it was about 8 inches long and 3 to 4 inches wide. So, each card can store one line of instruction. If my program has 100 instructions, there will be 100 such cards. Now, when I want to run a program, I have to submit that deck of cards to the operator. Operator would put that deck of card on a card reader machine. That machine would read the cards one by one. Then the CPU would be reading the values and trying to execute the code, whatever. And then there was a printer, the output was getting printed on the printer. So, you see, majority of the time here was being taken up by the process of reading the cards and printing on the printer, because the reader and printer were much slower as compared to the hardware inside the CPU. So, due to this large setup time, reading the cards, printing on the printer, the CPU utilization was very low. So, because of that, slight improvement was suggested. The concept of batch processing came up to improve on the CPU utilization. So, what was done here is that similar jobs were batched together. Like you see, that time the most commonly used programming languages were Fortran, COBOL and so on. Let us say all the Fortran programs were put all together, that was a single batch. The advantage is that the Fortran compiler is required to be called only once, because Fortran compiler itself was residing on a disk. They have to load that disk for the Fortran compiler, and if there are 5 programs that all want to use the Fortran compiler, they were loaded only once and they were run together. So, the operator submitted the whole batch together, so that at least the Fortran compiler's overhead was means incorporated only once. So, 5 times you do not have to load the Fortran compiler. Okay. So, the typical operation of such a batch processing system was like this, that the user submits the job, as I said, to the operator, typically in the form of a deck of punched cards. Operator will place a batch of several jobs, let us say several Fortran programs on a card reader, that is the input device, and here a very rudimentary form of operating system emerged, that was called a monitor. The first version of operating system was called a monitor. The monitor program controlled the execution of each program. See, diagrammatically you see here, the user programs was submitted to the operator. The operator divided the programs into different separate batches. Let us say one batch for Fortran, one batch for assembly language program, one batch for COBOL and so on, and the batches were submitted to the computer system one by one. Okay. This was how the programs were fed to the computer system. Now, some benefits of the batch processing system, as I said, is that the setup time was reduced by grouping similar jobs into batches. Setup time includes not only the process of reading from the card reader, but also the process of, let us say for Fortran programs, loading the Fortran compiler. That time the size of the disks were I think 18 inches in diameter, very large. Those disks have to be loaded on the disk reader, and then the cards have to be fed, and then the process started, process of reading the cards, compiling and running. Okay. This was the so called setup time. Now, if we put them into batches, once the Fortran compiler is loaded, there is a possibility of automatic job sequencing. Now, operator intervention is not required. Let us say there are 5 or 10 programs one after the other, they will be running one after the other automatically. But one thing is required, how to tell that where my job ends and the new job starts, where my one program ends and a new program starts. That time the programs used to be called jobs. Okay. So, the concept of job control language or JCL came up during this time. These are also sometimes called control cards. On some cards there are some special instruction, like let us say / job. Job means a new job is starting, a new program is starting. / for means I need the Fortran compiler, you need to load the Fortran compiler. Run means now you run your program. Data means now my data is after this card, and when everything is done, last is end. So, these are some special control cards that are also inserted along with my program card. The main problem here was that everything is fine, because the IO devices were very slow, still the CPU utilization was not good enough, it was rather poor, because most of the time CPU was waiting for either the card reader to read the cards, or the printer to print the output. Now, this resident monitor, as I said, this was the first rudimentary operating system which was proposed. Here in the memory, this is the picture of the memory, this is memory, main memory. So, in memory, in one part of the memory, some components of the operating system which is called a monitor was loaded. They contained the interrupt drivers. Whenever an interrupt comes, what will happen? The device drivers for card reader, line printers, scanners, plotters, job sequencing. So, reading those control cards and one after the other what to do, how to do, JCL, job control language interpreter, all these things were there as part of the monitor. So, here the role of the operating system was very simple, just sequencing one after the other, just that, and the remaining part of the memory was left for user program, typically one program at a time. Okay. So, initially when the machine is switched on, the control is with the monitor, monitor is trying to read the next set of programs, it will load the next program into memory and transfer control to it. So, when a job is again completed, indicated by the JCL, let us say / end, control will transfer back to the monitor. So, this mechanism, this allows minimum idle time between jobs, because it allows automatic transfer from one job to another using those job control language cards. But again, because the IO devices were slow, still the CPU had to wait for a long time. So, some years later, see, in the first generation the hard disk was not that developed, the disk was very expensive and disk was also, the capacity was very low. Now, disk technology became better and a new concept came up which is called simultaneous peripheral operations online, in short spool. This concept developed, as I said, with the developments in hard disk technology primarily, because one thing is true, the data read write speed of a hard disk was much faster as compared to the card reader and line printer, as compared to the input output devices. So, if I want to read something from the disk, that will be much faster as compared to reading something from the card reader. Similarly, writing to a printer would be much slow as compared to writing to a disk. So, the concept of virtual card reader and virtual printer emerged, and there was a concept of an auxiliary processor. Earlier we had a single CPU, now here we were having one CPU, main CPU, and one auxiliary CPU, one smaller CPU. And this concept of spool became so much popular. Even today, this term spool is used as a verb. We say that we are doing spooling, we are using a spooler, but actually spool stands for simultaneous peripheral operations online. As I said, we use two processors, main CPU and auxiliary CPU. Let us see how it works. First, the task of the main CPU. Main CPU, what it does, see here the idea is that it is assumed that my jobs, the programs, they are not being read from the card reader, they are already there on the disk, I will read them from the disk. So, let us first see what the auxiliary CPU is doing. The auxiliary CPU will be reading the jobs from the card reader and store them into a disk. See, in the meantime, the main CPU might be running some other program, and while the main CPU is running some other program, the auxiliary CPU is reading some next programs from the reader and storing them onto disk, and that space in the disk is called the virtual card reader, virtual reader. Similarly, there is another task of the auxiliary CPU. Some information to be printed that is kept in the disk. It takes those information from the disk and sends it to the printer for printing. This is the virtual printer. So, what does the main CPU do? Main CPU will read the next job, but not from the card reader, from the disk, from the virtual card reader. It carry out computation and print it. Where to print? Not to the printer, but to the disk, to the virtual printer. So, because the main CPU is only interacting with the disk, not with the IO devices directly, not with the card reader or printer, the overall speed improves greatly, the CPU utilization improves greatly. So, diagrammatically I am showing this, you see it will be more clear. The auxiliary CPU is reading the programs from the card reader and storing them into the disk. This is your virtual card reader, VCR, let us call it. The main CPU reads the programs from the virtual card reader, not from the card reader directly, and after computation it will print something, but it will print it, dump it to the disk. So, whatever it wants to print, it stores on the disk. This is your virtual printer, VP. And the auxiliary CPU, whenever it gets the time, it takes whatever is there on the VP and sends it to the printer for actual printing. So, you see the operation of the main CPU becomes much more efficient, because it need not have to wait for the slow card reader and slow printer, and all its interaction is via the disk. The same thing happens in almost all computer systems today nowadays. The main CPU does not interact with the directly with the IO devices, rather it interacts with the secondary memory wherever required, just using this concept of spooling. Okay. But these were uniprogramming system, one program was running at a time. So, what was the main drawback of such so called uniprogramming systems? Uniprogramming means only one program is executing on the computer system at a given time. See, disk is faster than card reader, line printer, fine, but still disk is much slower than CPU. So, whenever the program required some input output operation, it was doing on disk. During that time the CPU was lying idle. Okay. So, still even with using this spooling, the CPU utilization is still very poor. Most of the time CPU is waiting for IO, right. This was one problem, because only one program was running at a given time. When a program gets blocked for IO, the CPU has nothing else to do, the CPU has to lie idle. So, one possible solution was that why only one? Load more than one program into memory at a given time, and when one program is waiting for IO, let us not keep the CPU idle, let us switch the CPU to another program, so that it can start executing that other program. And when the IO operation is over, maybe you can stop that other program, you can come back and continue. This is the basic concept behind multiprogramming, and the main objective of multiprogramming is to improve CPU utilization. This is the main objective of multiprogramming. So, for the multiprogramming system, as I said, the basic idea is that if you look into the memory, this is your memory, several jobs are kept in active state in memory at the same time. That time we did not call them as processes, we called them as jobs. Let us say call them as job 1, job 2, job 3. Let us say there are 3 jobs. They are loaded into memory at the same time, and the CPU is multiplexed or shared, sharing is multiplexing among the active jobs. The idea is that whenever one job is waiting for the IO, some other job may start its execution on the CPU. So, here you see the role of the operating system is starting to become more crucial, more critical and more involved, because now you see in memory there are multiple jobs which are loaded. So, the problem of security comes in, okay. Protecting the address space means the memory area where a job is loaded. The address space of one job from another job must not be able to write something on my address space by mistake. Also, the operating system must decide which job to run next, which job to make wait till the other things are over. So, there is a concept called CPU scheduling which also emerged. CPU scheduling means there are multiple options available to you, multiple jobs available to you at a given time. Operating system must decide which job to execute next. That is the role of CPU scheduling. Okay. So, let us look into the protection issue here, spend a few minutes here. Let us try to understand one method how this memory protection can be provided, can be enforced. Let us say on the left side I am showing the memory map. Suppose a part of the memory is occupied by the operating system and there are 4 jobs loaded in the memory. So, what I am saying is that when a particular job is running, I must, let us say job 2 is running, suppose job 2 is running. What I must enforce is that, so when the instructions of job 2 are being executed, it should not be allowed to access any memory location beyond this. If it tries to access any address locations inside job 1, job 3, job 4 or some part of the operating system, it should not be allowed to do so. So, on the right side one simple mechanism is mentioned using which you can enforce that, using something called base register and limit register. You include some additional, you can say, hardware inside the CPU. Let us take an example. Suppose job 2, I am talking about job 2, right. Job 2, let us say it starts from memory address 1000. Job 2 starts from memory address 1000 and let us say the size of the job 2, let us say 2000 words or 2000 bytes, whatever, 2000 words. So, it starts with 1000, the size of the job is 2000. So, what I do is that before I start running job 2, I load my base register with the starting address of the program, that is 1000, and I load my limit register with 2000. And just one thing, you see, the CPU whenever it is generating an address, it is generating the address with respect to address 0. With respect to address 0 means it is assuming that job 2 is starting from address 0. So, you see, if it is starting from address 0, so means 0 up to 2000, right, size is 2000. So, this will be the range. So, what it is doing, I mean whatever address CPU is generating some address, right. First it checks whether the address is less than the limit register or not, whether it is within that 2000 range or not. If it is yes, fine, it goes to the next step. Then it adds it with the base register, so it gets the actual address 1000 is added, and then it accesses the memory. This is addition, this is an adder. But if it is beyond the limit register, that means you are trying to access memory beyond this limit range. You generate an exception interrupt and the program is not allowed to continue. See, this method has another advantage. Suppose later on you want to move some jobs in the memory. Let us say job 2 is shifted to some other part of memory. Let us say instead of 1000, now the starting address becomes 5000. So, the only thing operating system needs to do is that only the base register it has to change to 5000, nothing else changes. This is one simple mechanism, we shall again repeat it later, do not worry. When we discuss memory management in detail, we shall discuss all these things again. This is one method using which you can provide means adequate protection of memory of a job address space from other jobs. Okay. All right. Now, with respect to multiprogramming, let us take a very simplified example. Suppose consider job 1, consider job 2. Suppose my job 1 is like this. Job 1, I am just showing it like this. I am writing CPU means it is running on the CPU, it is executing some instructions on the CPU, but at this point in time it needs some input output. So, it cannot continue executing instruction. So, here it is waiting for IO. After the IO is complete, it again starts running some instructions CPU. At the end again some IO. Let us say this is how this program is. Let us say you do not worry about the units, the CPU time is 3, usually IO time is much more. So, IO time is let us say 10, CPU time is 4, IO time is 20. Let us say job 2 is another one. Similar, I am not showing to scale, it is maybe let us say again it is similarly CPU IO, again CPU IO. Let us say for job 2, the CPU initially CPU time is 2 time units, then IO is let us say 15, then CPU is let us say 7, then IO is let us say 12. Now, if you run these programs one after the other, let us say, then J1 will take how much? 3 plus 10 plus 4 plus 20. Total time will be how much? Total time, if you run them one after the other sequentially, J1 will take 13, 17, 37 time units, and J2 will be requiring 84, 36 time units. So, if you add them up, total 73 time units, this much time is required. But now if we use microprogramming, what will happen? Let us say here I am showing it in this fashion, J1, J2 I am showing this thing, and this is my axis of time, Suppose J1 starts first. So, J1 runs on the CPU for 3 time units. Okay. Till then J2 is not started yet, and after this one J1 will do this IO 10, this IO for another time 10. So, it will be 10 plus 3 13, then CPU again 4 more, 13 or 4 17, and again IO 20 more. So, 37. This is normally, as I said, J1 30. Now, think about J2. So, earlier J2 started only after J1 was over, but now what we are saying here, as soon as J1 is doing its IO, CPU has become idle. So, J2 can start its CPU execution here itself directly, CPU. This 2 units of CPU time, it can directly do it here itself. And as soon as J1 has got its CPU again, so the IO devices are free. So, J2 can start its IO operation here. So, here IO operation would be how much? 15, and also this CPU of 7, this can also be, and lastly IO of 10. See, the idea of what I am trying to say is that you see here now there is overlapped execution going on. When J1 was doing IO, J2 is executing some instruction. When J2 is doing some IO, J1 is doing some operation. Okay. Of course, here overlap will not be there, here I am showing overlap, this will not be there. So, the idea should be clear to you that microprogramming means the 2 jobs or 2 or more jobs, they are carrying out some kind of overlapped execution. When one of them is using the CPU, the other one can do its IO operation. When one of them is doing the IO operation, other job can use the CPU. That way the overall time, earlier it was 73, in this way it will be much less than 73. That is the basic idea of what I wanted to say. Okay. So, but for implementing multiprogramming, a few other hardware support is required from the processor side. Firstly, IO interrupt was already there. In addition, you need direct memory access DMA controller, because here you are trying to overlap CPU and IO operations. And if you recall, direct memory access is a mechanism through which IO devices can directly transfer data to and from memory. That is very much required in this kind of an approach of multiprogramming. So in addition to IO interrupts is required, because after IO operation is over, the CPU must be informed that IO is over, and DMA is required for direct transfer of data. And secondly, to prevent that some program must not unnecessarily hog the CPU, that it runs and somehow it falls in an infinite loop, the other job does not get any chance to execute, it has got running in a loop. So, you can introduce the concept of timer. You can load the timer with some maximum value, go on decrementing it. As soon as it reaches 0, CPU will be interrupted. So, operating system gains control and check that how much time the process has taken, the job has taken. So, if it has taken too much of a time, there must be something wrong. So, the job might be stopped, something like that. Okay. So, here the concept of memory management also becomes important, because there are multiple programs in memory, and as I had already said, memory protection is also required. Not only this hardware support, some software support is also required from the point of view of the operating system, because now there are multiple programs that are ready to run at a given time. So, which program to run first, that decision has to be taken by the operating system, that is called CPU scheduling, and that is a software decision, because operating system is a software. And in case there is some resource conflict, multiple processes want to use the same resource, the operating system should also ensure that there is no deadlock. Deadlock means there is a wait cycle kind of a thing, we shall see later. So, none of the jobs will be able to proceed because of this kind of a deadlock scenario. Okay? Fine. Now, the other kind of operating systems, very briefly we will look at it. One very commonly used system that we will look at, we encounter, is called a time sharing system. Time sharing system is different from a multi-programming system. In multi-programming, we switch from one job to another only when the first job has gone for IO, right. Otherwise, the job 1 would have continued. But in time sharing system, it is not like that. Here the idea is that we provide each running program with a small time slice in a cyclic fashion. Cyclic is sometimes also called round robin. Cyclic means, suppose there are 4 jobs running, okay, that there are 4 jobs. You first run the first job for some short time, then the second job, then the third job, then the fourth job, again come back to the first job. You repeat this process, giving some small time to each of the job. That small time can be a few milliseconds, it can be 2 milliseconds, it can be 5 milliseconds, whatever. This is shown diagrammatically in this figure. Let us say this user 1, user 2, user 3, user 4, there are a number of users whose programs are there, user programs are running, they are shown as those black dots, and there is one CPU. And this red arrow indicates that currently user 3 is running, the program number 3 is running. We are saying that this program is active. Now, after this program is running, this user 3 will be given some short time slice, as I said, let us say 2 milliseconds or 5 milliseconds, whatever. After the time slice is over, the CPU will be switching to user 4, it will stop user 3, it will be switching to user 4. User 4 was ready so far, ready means it was ready to run. So, once the previous program's time slice is over, it will switch to another program which is ready to run, and this process will continue. Okay. In this way, multiple programs can run apparently simultaneously, but not actually simultaneously, in an interleaved fashion. But every program, every user is given an illusion that the CPU is running my program only, because this small time slice 1 or 2 milliseconds is given. So, when I sit on a terminal, I find that when I give a command, in a fraction of the second I am getting my response. So, I get a feeling that, well, the computer is only listening to me, but actually it is not like that. Computer is listening to 10 other programs, but given let us say 1 or 2 milliseconds each. So, when my turn comes again, I am getting back the response, but because it is happening so fast, I am not understanding the difference. So, it is basically creating the illusion of a virtual processor to every user. Every user is feeling that I have a processor of my own, I am owning the processor, but actually it is not. The processor is being shared by all the user programs, right. This is the basic concept of time sharing system. This is very important in the present day context, because nowadays all the users are sitting on the terminals and interact with the computer system. So, they want a very fast response time. Whenever I type something, I should get back my response first. But multiprogramming, what we just discussed some time back, that was not interactive, that was similar to that batch processing, where the jobs were submitted in batches. CPU utilization was most important. So, that multiprogramming concept came from that. Okay. And so, for time sharing system, as I said, that the users are all sitting in front of the terminals. That is why user response time is the most important parameter that you want to minimize. And in order to give that equal time slice, the most important hardware resource you need is the timer. So, you have to initialize the timer in such a way that down count to 0, that will happen let us say after every 2 milliseconds. So, you load the value of the timer accordingly. So, after every 2 milliseconds there will be an interrupt generated, and whenever there is an interrupt generated, operating system will be waking up, operating system will be finding out which is the next process in the round robin queue, it will start the next process, again reload the timer and continue. Okay. But of course, remember one thing, a process may be given a time of let us say 2 milliseconds, but maybe before that it may issue a system call and block itself voluntarily on its own. It may need some IO or some other operations. It may not require the CPU that time. So, maybe it will release the CPU earlier also, but maximum that much time, 2 milliseconds or that slice, time slice. Next, there is something called real time operating system, which of course we do not see in our conventional computer system that we use. They are used in some very specific environments. In these environments, they are characterized by the property that the inputs to the computer systems, they are typically coming in the form of some events, and these events are often generated from outside the system, not someone sitting at the computer and giving. They are generated mostly external to the system, and the important thing is that whenever such an input is coming, they must be processed in a short time, or there can be some deadlines. Within that deadline they must be processed. If you think of the typical applications, you can understand why these short time or deadlines are important. Think of a command or control system. Let us say in a defense scenario, there can be command and control system where you are monitoring the missiles and aircraft from the enemy territories. So, if your radar detects any such, so immediately you will have to respond, you will have to retaliate, right. So, you cannot wait, you cannot say that well let me complete the present job, after that I will do it. There has to be a very hard deadline for that. Similarly, airline traffic control system. So, continuously you are monitoring the airline traffic, which airline is coming and going. So, you are continuously monitoring and modifying and adjusting the routes of the aircrafts. So, any mistake there can be very catastrophic, right. Similarly, you can have a patient monitoring system where you are continuously monitoring the health of a patient, various parameters you are measuring, and depending on what you measure, you are also giving some corrective things. Now, depending on the kind of the system, your severity, the short time, deadline, all these things, the degree of that can vary. Depending on that, this real time operating systems can be broadly classified into 3 classes, you can say 3 types. First, you can say something called hard real time operating system, hard RTOS. Hard means the system specifies some deadline, that if my input comes, the input must be processed within time t, must be processed. That is a hard deadline. Now, that deadline, that time is how much, that depends on the problem. It can be a few milliseconds, it can be a few seconds, it can be 1 minute or whatever, but whatever time is specified, it must be done within that time. Maybe in a chemical plant, there are often requirements that something has to be done only after a chemical reaction has taken place, and we cannot wait after that, you can do it immediately, have to do it immediately. So, those are examples of hard real time operating systems. Soft real time operating system means it is negotiable. Like for a patient monitoring, you can see that blood pressure of a patient is dropping, but it is not that you have to respond within 1 millisecond, maybe 1 minute, 2 minutes is also fine. So, let the doctor come, let the doctor respond, it can raise some warning. And firm real time operating system is something where there is a deadline, but the deadline is not that strict like hard RTOS. You can negotiate and you can adjust the deadline depending on the scenario, you can adjust it a little bit. So, various kinds of such RTOS or real time operating systems have been designed, are in use. Depending on the environment or application where it is deployed, you can specify the requirements of your design accordingly. Okay. And the last kind of operating system that we shall be talking about here is what you all see with us, mobile operating system. So, all of us today carry smartphones, and you see on a smartphone there are a variety of operating systems which are running, starting from iOS, then Android, and various other versions are there. Okay. Now, you see in a mobile operating system or a mobile system, the user interface whatever is provided to a user, the requirements are entirely different. So, when you are sitting in front of a terminal and working on a computer, you want fast response, but when you are working on a mobile, you are in a meeting, you are doing something, the user satisfaction is of paramount importance. So, the user interface must be as smooth as possible. User interface is very important, but in the other kind of systems, the user interface is not that important, rather whatever you are doing, whatever command you are giving, responding to that becomes more important. And another difference is that in mobile operating system you see, sometimes it happens, I told you earlier that whenever a situation happens when there are too many processes running, too many programs running, memory is full. So, you have to swap out some process to secondary memory, later on bring it back, because the idea was that those programs have to be run, but let us temporarily swap out, it will take a little more time, later on will run. But in mobile operating system you may have encountered something that sometimes some of the apps crash, suddenly they stop running, you will have to again restart them. That is what mobile operating system do as a policy matter. To improve upon the user satisfaction index, the user interface, whenever it finds that memory is becoming low, there are a large number of apps which are requesting for memory, it will forcibly kill some of the apps, it will forcibly stop some of the apps, not temporarily move it to swap. So, it depends on the application scenario basically. For a mobile phone, none of the applications are that critical in that sense. So, some of the application like a music player for example, you can kill it, you can always restart it later, that is not so critical, right. So, basically these kind of mobile operating systems which run on smartphones or tablets typically, they provide some kind of an interface between the hardware components whatever is there inside my mobile phone and of course, the software functions. In addition, we sometimes forget that the mobile phone can also, we can make some phone calls using that, we forget that. So, managing cellular and wireless network connectivity and phone functions, these are also additional responsibilities. So, as I said, usability is most important and also availability. Your phone must not hang, that is very least desirable, but still some of the phones hang sometime, that is very irritating to the users. So, some of the very commonly used mobile operating system as I said, they are the Apple iOS, Google Android, and there are so many versions of this Android on various different smartphone platforms. So, what we said is that there are so many different kinds of operating systems that have been designed, that are being deployed for various different kinds of application and environments. Now, when you are thinking about designing an operating system, you must be aware of what environment or what kind of scenario you are looking at. All features and functionalities of an operating system may not be required for all of them. For some of the environments, security and safety may be more important as compared to the others. So, it really depends. A single operating system cannot cater to all the requirements and all different kind of scenarios that you normally see. So, with that we come to the end of this lecture now and also this module. In the next module we shall be looking at some more details about the concept of the programs in execution, I said the processes, and also a related thing called threads, processes and threads. These will be the topic of our next module. Thank you.